SwayamPrabha. Digital India. Educated India.
Hello, we will continue our discussion on central force motion in this lecture, and we are going to now look at the two body problem. Till now what we were discussing was the motion of a single point mass about a central gravitating mass which is essentially fixed. But today we will start by discussing this two body problem, that means both the bodies are free to move unequal masses, and let us see how the dynamics evolves. Then we are going to look at tidal dynamics, how tides form and why do they form, and some features of tides. We start with this two body problem. Consider this figure where I have shown two point masses, one capital M which is larger and small m which is smaller mass. The position vectors in some inertial frame of reference is indicated by r1 vector and r2 vector for the small m and the capital M, and r vector is from capital M to small m. If we consider this system and write down the equations of motion by using Newton's law of gravitation, Newton's second law and third law, then we get these two equations of motion for the two point masses. For the lowercase m mass with lowercase m, I have r1 double dot m, r1 double dot is minus of g capital G which is the universal gravitational constant, capital M small m by r cube into r vector. Now this point we have discussed before, it is r square. Normally this is as a vector, this force is minus g m m by r square times unit vector r. Now this unit vector r I am writing as r vector by r, and this r gets coupled here to give me r cube, and unit vector and this vector r sits here. Similarly, for the uppercase m mass, it is r 2 double dot m times capital M times r 2 double dot is equal to now g m m by r cube into r, because of equal and opposite forces acting on these two mass points. Now if I divide the first equation by lowercase m, second equation by uppercase m and subtract, if I subtract, why am I subtracting? Because I want to know the dynamics in terms of this r vector. Therefore, I get r1 double dot minus r2 double dot is equal to minus g m m by r cube, and then within brackets 1 over small m plus 1 over capital M times r vector. This is straightforward algebra. Therefore, I can now recast this equation. I can recast this equation in this form, where I define mu. From here I get the definition of mu, which is small m times capital M by small m plus capital M. This is known as reduced mass. Therefore, our equation of motion is now reduced mass times r double dot, this r is this vector, reduced mass times r double dot is minus g m m by r cube into r vector. Thus, now we have an equation of motion which is in terms of r, the r vector. Now, I can recast the reduced mass in this form, small m by the ratio of small m is to capital M plus 1. Therefore, in the limit when small m by capital M goes to 0, what happens? When small m by capital M goes to 0, this term goes to 0, and therefore, this mu goes to small m. Therefore, our equation in the limit equation becomes which is the same equation which we have solved. And what have we done by taking this limit? We have said that the capital M mass actually goes to infinity, or there is hardly any motion. In other words, there is hardly any motion of the greater mass, the capital M mass. Therefore, we get back what we were discussing under central force. This is two body problem, and it reverts back to the central force motion problem in the limit small m by capital M goes to 0. And this point we had discussed right at the beginning when we started discussing central force motion. We were representing in this analysis, we were representing the whole dynamics in terms of an inertial frame which is located somewhere, its origin is somewhere. We can also recast this dynamics in terms of the center of mass frame of this system of two bodies. Let us look at the center of mass frame formulation. This is the standard equation which I just now wrote for the two masses small m and capital M. If I add these two equations now, if I add these two equations, then I obtain this relation. The right hand side addition of the two right hand sides is 0. Therefore, left hand side it is small m times r 1 double dot plus capital M times r 2 double dot is 0, is a 0 vector. What this means is the center of mass of this system is non-accelerating. It is non-accelerating. It could always be fixed, therefore, since it is non-accelerating means it can at most have a constant velocity. Therefore, I can always switch to an inertial frame which is moving with the center of mass, and in that frame the center of mass becomes fixed, and that is what the center of mass frame is. Now, how do we say that this means that the center of mass is non-accelerating? It is because the way we define center of mass, how do we define center of mass? Suppose in this figure I would like to represent what is rg, the position vector of the center of mass, let us say. So, it is from this origin to the center of mass, this vector is rg. Then how do you define rg vector? Rg vector is defined as summation of mi ri vector by summation of mi. This is how center of mass coordinate is defined, the position vector of center of mass is defined. Now, everything is constant here except these masses are all constants, that is what we assume. Therefore, I can start taking derivatives of this equation. Therefore, I can take the first derivative and it becomes in terms of velocity of center of mass in terms of the velocity of individual point masses. If I take the second derivative, is the acceleration of the center of mass, acceleration of the center of mass in terms of the accelerations of the bodies involved. Now, if this summation goes to 0, if this summation goes to 0 as it has occurred here, what it means is that rg double dot must go to 0, because summation of mi is not 0. Therefore, rg double dot must be 0, which means the center of mass is non-accelerating. This implies center of mass is non-accelerating, and if it is non-accelerating, which means it may at most have a constant velocity. Therefore, I can switch or shift to another inertial frame in which the center of mass is fixed. Now, I use two vectors eta. What are these vectors eta? I define this vector eta 1 and eta 2 as vectors starting from the center of mass G of the system and going to the individual masses. Therefore, eta 1 is from G to small mass and eta 2 is the vector from G to capital M. These are eta 1 and eta 2, and then I can write R 1 vector as R G vector, which is the position vector of the center of mass. Now, remember that in the center of mass frame this R G vector is fixed, it is constant, and this plus eta 1 vector. Therefore, R 1 vector is nothing but R G vector plus eta 1 vector, and similarly R 2 vector is R G vector plus eta 2 vector. And if I start differentiating, taking time derivative, this would imply R 1 dot is equal to eta 1 dot and R 2 dot is equals to eta 2 vector dot. Why? Because R G we have shifted ourselves to a frame in which the center of mass is fixed. Therefore, R G is a constant vector, and hence R 1 dot is eta 1 dot, R 2 dot is eta 2 dot, and therefore, double dots are also the same. So, R 1 double dot is eta 1 double dot, R 2 double dot is eta 2 double dot, and that is what I have used in this step. Now, these vectors eta 1 and eta 2 can be written in terms of that R vector which I just now showed you. Just a moment ago I had showed you this vector R. This R is from capital M to small m, and I can write eta 1 vector as eta 1 magnitude times unit vector R, while eta 2, which is opposite, it starts from G and goes opposite to R vector to capital M. Therefore, eta 2 vector is magnitude times unit vector R in the opposite direction minus, that is how this negative sign comes about. Therefore, by substituting these expressions in here, I will obtain small m times magnitude of eta 1 minus capital M times magnitude of eta 2 is 0. And now, I use these things in my equation of motion. One step here, eta 2 can be written as m small m by capital M eta 1. These are magnitudes, eta 1 and eta 2 here are magnitudes of those vectors eta 1 and eta 2. Okay. Now, for the small mass, m eta 1 double dot is therefore minus g m m by, now this I can write as eta 1 plus eta 2 whole square times unit vector eta 1. This is unit vector eta 1. This is the total distance between small m and capital M, because eta 1 and eta 2 are magnitudes, remember, and eta 2 now I will replace with this expression and I will pull out eta 1. I will pull out eta 1, then what do I get? I get 1 plus small m by capital M whole square, and here I will get eta 1 cube. This is just by substituting this expression eta 2 in this bracketed quantity. If you substitute and simplify, this is what you will get. In a similar manner, you can simplify the second equation of motion for the capital M mass. Eta 2 double dot is minus g m, and this is small m by capital M divided by 1 plus small m by capital M whole square and eta 2 vector by eta 2 magnitude cube. And you should note the similarity in dynamics of the two systems. And here now what we have done is we have been able to represent these two individual mass dynamics of these 2 point masses absolutely independent of one another. Now, we can again ask the question, what happens if small m by capital M tends to 0? You will find that the first equation, this equation, if small m by capital M tends to 0, so therefore, this becomes 1 square, therefore, I get this equation from the first one, simplified equation, and this coincides with the equation of the central force problem. You can see that this can very easily recognize that this is the equation of motion that we use in the central force motion, where one mass is held fixed, the gravitating mass is held fixed, and eta 2 double dot is 0, which means that the central gravitating mass now has 0 acceleration in the center of mass frame. Therefore, this boils down to the central force motion problem. Thus, if the small mass is much smaller than the capital mass, the central force motion problem is good enough to deal with the dynamics. So much for central force motion problem. Let us now move to tidal dynamics. What are tides? Those who live or have visited the ocean shore, or you have seen the seashore for a considerable period of time, you will note that there is periodic rise and fall of the water level. This periodic rising and falling of the water level, ocean water level, at a particular location near the sea is known as tide. And another effect that you might see in many places is advancing or receding shoreline. The sea seems to recede at some point of time, and again it comes back at some other point of time. So, this advancing and receding coastline is an effect of tides. And near the mouth of the rivers, where the river meets the sea or the ocean, you will find that the water level in the river also rises during high tides, and it falls at low tides. And you might have noticed that boats and ships do not want to sail out when it is low tide, because they might get stuck. Okay. Now, why do we have tides? We have tides essentially because of the gravitational attraction of the sun and the moon, and this is what we are going to now analyze. Now, to analyze this problem, this is essentially a very complex problem, but we are going to simplify the problem by making some assumptions. The first assumption that we make is that the sun earth distance is fixed, it is constant. In other words, the earth is rotating on a circular path around the sun, which is not a very bad approximation, I would say, because the eccentricity of the earth's orbit is very low, very close to 0. We will assume for this problem that it is on a circular path, earth moves on a circular path around the sun. Therefore, this distance is essentially fixed. The second assumption that we will make is that Earth's axis of inclination, which is roughly 23.4 degree, is neglected. We will neglect. In view of that, this figure that I have drawn is the top view seen from the North Pole, let us say, seen from much above the North Pole from a great distance. We are seeing both the sun and the earth. I cannot draw the sun, of course, I have marked it as a point, and earth I have drawn as a circle, this circle is the equatorial circle. Remember, we are looking from the top and there is no inclination, therefore, this circle is the equatorial circle roughly. And Earth is spinning about its own axis. This omega represents, this small omega represents the spin of the Earth, this capital omega represents the rotation of the Earth around the sun. Let us have some feeling of the numbers which are involved in this calculation, though we are not going to do any numerical calculation, but you must have some idea of what the numbers look like. The radius of the Earth is roughly 6,400 kilometer, which translates to 6.4 into 10 + 6 meter. The sun earth distance is 150 million kilometers, which is 1.5 into 10 = 11 meter. Mass of the sun is 2 into 10 to the power 30 kilogram, and omega, the spin speed of the earth, which we have calculated even before, is 7.27 into 10 to the power -5 radian per second. That is the spin speed of the earth. Let us now imagine a particle P. This could be a water particle or a collection of water particles. So, P essentially represents a small mass of water. Let us try to represent its acceleration as observed by an inertial observer, and then we will try to write its equation of motion. Acceleration of this particle or mass of water is equal to acceleration of the earth plus AREL. This is our master equation which we have discussed many times in kinematics. So, acceleration of P is acceleration of earth plus AREL plus alpha cross EP. What is EP vector? E is the center of the earth, as you can see from this figure, and P is the particle, location of the particle. Alpha is the acceleration of the spin, which is 0 of course. Earth spin is constant, therefore, alpha is 0 already, plus omega cross EP. So, spin of the earth vector cross spin of the earth cross EP plus 2 omega cross VREL. Now, here I will make this assumption, simplifying assumption, that this particle or little mass of water that we are considering is initially not moving, though we know that oceans are always dynamic, but for simplicity of this whole calculation, we assume that this motion is very small or VREL is very small, essentially static with respect to the earth. You know, VREL is the velocity as measured by an observer on the earth of this mass of water. This VREL we will assume to be 0, that initially it is not moving, and then let us see what the acceleration of the particle is from the dynamics, and then it might be different, but that will be very small. So, we are neglecting it. In any case, omega, the spin of the earth, that is any case very small. Okay. Now, we put in the expressions. Now, acceleration of the earth, because of its rotation on a circular path around the sun at a constant angular rate capital omega, is nothing but the normal acceleration. You see, it is, we are using this coordinate system, this is y, this is x, which is centered at the sun. We are assuming that the sun is static. We fix that coordinate system, Cartesian coordinate, at the center of the sun, and we are writing the acceleration of the earth center, and that is nothing but the normal acceleration or the centripetal acceleration, and that is in the negative I cap direction. Centripetal acceleration is towards the sun and negative I cap direction, and its magnitude is capital omega square r s e. This is a standard expression for the centripetal acceleration, there is no tangential acceleration, okay, plus AREL vector, which actually is what we observe or measure on the earth of that particle P, minus omega square r e. So, this is the centripetal acceleration term. This acceleration term will be omega square r e, and its direction is minus E p. This vector, this is the unit vector E p. This is the unit vector E p, and this E p vector has magnitude r e, radius of the earth, and its direction is this negative cos theta I cap plus sin theta j cap, which you can find out. This angle is theta, which is marked in the figure. Therefore, E p cap is nothing but cos theta I cap plus sin theta j cap, and the centripetal acceleration of this particle, because of the spin, is therefore in the negative direction of this unit vector, and magnitude is omega square r e. Now, we are going to write the equation of motion for this particle p. Mass times acceleration, inertial acceleration of the particle must be equal to the net force acting on the particle. What are the forces acting on the particle? The first one is the weight, which is in the minus mg n cap. Again, this n cap is nothing but E p cap. This n cap is nothing but E p cap, unit vector in E p direction. So, minus E p cap is the direction of gravitational force, and magnitude is mg. So, mg times minus n cap or E p cap. So, minus mg n cap. The second force that is acting is because of the sun, and for this I have written the Newton's law of gravitation. Now, this force will act in the direction of S p. What is S p? This is the vector S p, that is the vector S p, and I have used that to write down the gravitational attraction on the particle due to the sun. Thus, this is our equation of motion. Now, we are going to express these quantities. I am going to plug in the value of acceleration of p and separate out mass times acceleration, relative acceleration. Why this? Because on the right hand side, whatever goes is the force as felt by that particle or the quantity of water being on the earth. So, mass times ARL, this dynamics is going to govern the dynamics as observed by an observer on the earth, which is a non inertial frame here. Therefore, the acceleration of the particle as measured by an observer on the earth will be ARL, and mass times ARL must be the forces then acting on the particle. And when you plug in all these values, what you will observe, this is pure algebra, you will get whatever I have written on the right hand side. This term, all these terms come after you have plugged in these expressions. Therefore, this mg n cap, you have n cap, and you have terms from here, because I have written mass times ARL. So, this and these things therefore go to the other side and they contribute. For example, this term comes from here. Okay. Once you have done all those things and simplified, this is the expression on the right hand side. Now, this is the effective force acting on the particle. Here, this expression is roughly equal to g. Remember, omega is 10 to the power minus 5, spin of the earth is 10 to the power minus 5, and spin square is 10 to the power minus 10, and then radius of the earth is 10 to the power 6. Roughly this will be 10 to the power minus 3 minus 2. something like this if you multiply. And so that is there is a correction. Now, if you want to do an exact analysis, you can retain this, or you can take this as g for simplicity. This term, last term, mass times omega around the sun, the omega of the earth around the sun square into r SE. Now, that this expression I can write in terms of, by equating the centripetal acceleration of the earth. This is the centripetal mass times centripetal acceleration. This is basically mass times acceleration of the earth is equal to the gravitational attraction because of the sun on the earth. This simplifies to this expression. Therefore, I get capital omega square r SE in terms of universal gravitational constant, mass of the sun, and sun earth distance. Therefore, I can replace this term, and that is what I am going to do next. Here I have done that and rewritten that equation of motion. Now, SP, the sun particle vector, this sun particle vector, this vector is nothing but sun earth vector plus earth particle vector, and that is what I have used to represent this. The magnitude turns out to be this, and when I plug in all these expressions into our equation of motion, this one, I get here a complicated expression. Now, you will observe here we have radius of the earth divided by radius the sun earth distance whole square. Now, if you calculate, I had given you these values, radius of the earth divided by sun earth distance, that turns out to be 4 into 10 to the power minus 5, and square of that will be something like 10 to the power minus 10 or 10 to the power minus 9, which is very small. We will neglect in comparison to this term, because this already has a 1. Therefore, if I drop that, then what I am left with in the in this denominator is this term to the power 3 by 2. Therefore, I will have 1 plus R e by R S e cos theta to the power 3, because there is 3 by 2 and there is a square here. So, this will be cube, which I take to the numerator and do an expansion and retain only up to first term, because R e by R S e is 10 to the power minus 5 order, and this is what I get. This is purely algebra approximation, and rest of the thing follows from here. If you simplify these expressions, then you arrive at this right hand side. So, mass times A rel is approximately equal to this on the right hand side. This I have written out here, and this I call F theta. On the right hand side, therefore, we have force. This has dimensions of force, and this is a function of theta. Therefore, at different points on the equator, we will have different force. Let us try to see what are these forces at 0 and pi, at theta equal to 0 and theta equal to pi, which means at this point and this point, this is theta equal to 0. What do I have? I have the weight which is acting in negative I cap direction towards the center of the earth, as shown by this arrow, and there is a small positive term in the positive I cap, which is indicated by this red arrow. This is at theta equal to 0. Similarly, theta equal to pi radian, I have the weight acting towards positive I cap direction and a small force which is acting in negative I cap direction, which I have again shown by this red arrow. Therefore, apart from the weight, we have these red arrows which are to be observed. When it is at pi by 2, at these two locations, this is at pi by 2 and this is 3 pi by 2, you will find the weight is always towards the center of the earth, of course, but there is this additional term which is because of our analysis, and at pi by 2 and 3 pi by 2 they are both towards the center of the earth, whereas at 0 and pi they are both, these additional terms are both away from the center of the earth. Therefore, what should we expect? This is the force that is acting on the particle at these points. What we expect is force field something like this. If you do a complete analysis for all values of theta, you will get the force vector, additional force vector. This is the additional force vector. Of course, weight is there, but and weight is the dominating force, but there is a small part that creates all the difference. And therefore, if this is the unperturbed sea level shown by the dashed curve, dashed circle, because of this additional force you will have a bulge. This is called the tidal bulge, and this is at the equator. This bulge that I have drawn is at the equator. If there is a person standing here, a person standing on the earth at this point of the equator at midday, at noon, standing here will observe a high tide. Ocean water has risen. After 12 hours, this person, because of the rotation of the earth, would move to midnight. So, from noon to midnight, and again the person will observe a bulge. Therefore, this tide has a 12-hour period. The tidal period has 12 hours. It is a 12-hour period. So, after every 12 hours you will see a high tide, or this portion is a low tide region. So, every 12 hours you will see low tide. Now, let us look at the effects of the sun and the moon. Because of the sun we have just now analyzed, we have high tides on the two opposite sides, on the sun side and opposite side there is a bulge, and low tide on 90-degree direction. Because of the moon, on a new moon, when the moon and the sun are on the same side, it is a new moon phase. So, it is exactly on the sun earth line, let us say, not exactly on that line, but it is a new moon day. Then just because of the moon, you will again observe the tidal bulge very similar to that of the sun. Even on the full moon night you will see a tidal bulge very similar to that due to the sun. And because of the nearness of the moon to the earth, the tidal bulge is more due to the moon. Moon has a greater effect on the tides. Therefore, the net effect of sun and moon taken together is a very large bulge, equatorial bulge, because both of them will reinforce the high tide. This is called the spring tide. The net effect is something called a spring tide, a very high tidal bulge or a very low tide. Whereas, if you have, this is again the sun, because of the sun you have tidal bulge. Now, the moon's location is 90-degree to the sun earth line. In that case, the tidal bulge because of the moon is rotated by 90-degree with that of the sun, and you will notice that they are in opposition. The moon tends to pull the tidal bulge toward itself, whereas the sun depresses it. Therefore, there is this net effect is diminished because the moon is more dominating. Therefore, the tidal bulge is more towards the moon direction. When the sun and moon effects are taken together, we have this neap tide when the sun and moon are 90-degree with respect to the earth. So, this is all about tidal dynamics. So, in this lecture we have looked at the two body problem and tidal dynamics. So, with that I will close this lecture.